Hello everyone, welcome to the next lecture. In this lecture, we are going to discuss small signal models of the diode. Okay, small signal diode. So we are gonna draw some of the approximations of the small signal model and how diode into the small signal model can be modeled as a resistor. We are gonna learn that, and we will see how such analysis could be used in different problem solving too. Okay, so let's start with the small signal diode. Um, so in this analysis, we will show that under small signal operation, diode at low frequencies. We are only doing a low frequency analysis, but not the high frequencies. So we will show that under small signal operation, diode can be modeled as a resistor. And probably you would have realized that by now, right? For example, if we are talking about this model like this, and if I will select any point here on this curve and assume it to be very small and draw a tangent here, this will become a linear characteristics in between B and I, which is equivalent to a resistor. So anyways, we're gonna discuss these details in today's lecture. So for a small signal operation, diode is going to behave as a resistor, can be modeled as a resistor. So we will discuss that in more detail, and this modeling helps with in simplifying and design of electronic circuits. So that's the reason why we are doing all of this analysis. Okay, so now consider the following circuit. Consider following circuit. For example, here's a circuit I have. Here is a resistor and a diode connected to it. Let's call this as VDD. Resistor, current ID is flowing through it, and a potential drop across the diode is VD. Now suppose VDD goes under small change. Let's call it as delta VDD, right? So let's assume that this VDD will undergo a very small change in its voltage value. We're going to call it as delta VDD. When that will happen, the current ID will also be changed by delta ID, and the potential drop across it will also be changed by delta VD. Right? So what we are interested in is finding these incremental changes. Right? We are interested in finding the values of these incremental changes. We're interested in finding what is the value of delta ID, delta VD as delta VDD when there's going to be a small change of delta VDD. All right, so if I have to model this further, I can further model this as, so here's my VDD. So this is VDD. Now assume that there's a small change in VDD, which I am representing here. Here's a resistor. Here's my diode. They're connected to each other. Resistance. So the current will become ID plus delta ID. There's going to be a small change in the current. And there is going to be a small change in the potential drop across the diode. So we can further expand the circuit something like this. We are now assuming that there is a small change in the VDD, which resulted in a small change in the ID, delta ID, and correspondingly the small change in the potential drop across the diode delta VD. All right. Now also assume that delta VDD is a time varying small incremental change. And let's look at that, how this will look like on the IV characteristics. All right. So on IV characteristics, so here is a current ID, here's a current VD. If I have to make this slightly just to show you, okay. Yeah, this is slightly more exponential. Okay, so I am going to redraw this thing. Okay. All right. This is more like it. So let's assume that we have, this is our exponential relationship of the p-n junction diode. Now let's assume that we are operating at this point. So this is VD, potential drop across the diode, and this is ID, our current flowing through the circuit. And so this was our operating point. We're going to discuss that more, but operating points are also known as bias points. Okay, now how we will analyze it. So let's see what does it mean to have a small change. So let's see that we are operating over here. So what I will do is, so I'm going to draw a very small tangent here, and once I'm going to draw a small tangent, I will see how will that changes all the values of VD and ID. Okay. Okay. So what is happening over here is we have a, so let's suppose this is a change in the current that we see, and the corresponding change in the voltage is represented over here. Now let's assume that in order to make sure that we are talking about very small changes, so let's assume that we are talking about this change from here to here, right? And we can call this as ID of t. This blue line is tangent at Q point. And these are time varying signals. And let's call the corresponding change in the voltage over here to be VD of t, right? So this is the incremental change in voltage VD, and this is also the incremental change in current. Now interestingly, we can see that as there are small change in the current will happen, that will produce a corresponding change in the potential drop across the diode VD. Another thing that we will realize that the change in the current is higher as compared to change in the voltage. Also, I don't have over here exactly the straight lines, but you can still see the difference, that the change in the VD is much smaller as compared to change in the ID. We're going to come back to this point again. So anyways, these are the incremental changes. Another thing to look over here is the slope of this tangent line, right? Okay, so slope of the tangent line. So how we can find the slope of the tangent line over here? Now tangent line is linear, right? So our ID will be equals to VD over R. And now this resistance, I'm going to call this resistance over here to be RD. I'm going to call this as a small signal diode resistance. So if there is a small change in the signal, keeping this tangent to be as small as possible at a point Q, we are ensuring that this line is a linear. And for that specific small signal operation, the resistance, the slope of this line can be equals to 1 over RD, where RD will be equals to the small signal diode resistance. Okay, we're going to discuss that in more detail. All right. So let's analyze this small signal. Let's solve that circuit that we have drawn over here, and let's analyze this small signal analysis a little more. Okay, so the voltage drop across diode is sum of DC voltage VD, right, which is around 0.7 in a constant voltage drop model, and time varying VD of t, right? So I can represent the total instantaneous voltage drop across the diode to be its DC voltage value plus the time varying VDT, right? So this is that time varying VDT, and we want to make sure that this time varying VDT is as small as possible. This will, so we want to make sure that the time varying ID is as small as possible. That is going to produce a very small VDT as well. Similarly, we can also see the total instantaneous diode current will be, so ID of t will be equals to IS e raised to power sorry, capital VD of t over VT, right? Now this VD of t is a sum of two voltages, so I can further rewrite it as e raised to power VD plus VD of t over VT. Now you can expand both of them. E raised to power VD over VT and e raised to power VD of t over VT. We can also see that. So this is our total instantaneous current. So we can see that in absence of the time varying component, right? So this is our VD of t was our time varying signal in the diode. So if that component is absent, right, so the diode voltage will become equals to VD, and we know that for this condition ID equals IS e raised to power VD over VT, right? So this is, so I am going to replace this value now over here. So the total, again, instantaneous diode current will become ID into e raised to power VD of t over VT. All right, so this is the total instantaneous diode current. Okay, so now we have to, now let's make an assumption. If amplitude of VD of t is kept very small, and this is what we are interested in a small signal operation, such that VD of t over VT is very, very smaller than 1, or essentially VD of t is very, very smaller than VT, then we can expand this equation, right? We can use Taylor series expansion to simplify. Okay, so we're going to expand this equation, this exponent equation of the instantaneous diode current, and we are making an assumption, and our assumption is that this time varying change across the diode is going to be very small as compared to the thermal voltage. Okay, so if that is with this assumption, right, so this is an assumption considering small signal, considering small signal operation. So if this is an assumption that we're going to make considering the small signal operation, then we can open up this equation using Taylor series. Okay, so if we will open up this equation using Taylor series, we will get id of t will become equals to id 1 plus vd of t over vt. So this is a expansion of the of that equation. Now this thing is called as small signal approximation and it's only valid when Vd of t is very, very smaller than Vt. Now we know that at room temperature Vt is usually 25 millivolts. So for example, we can say that Vd of t should be around 5 millivolts or so. So it needs to be pretty smaller than the Vt for this equation to hold. Now I'm going to further expand this equation. id of t equals id plus id vd over vt. Now similarly we know that id of t, which was the diode current, is equals to, if I will go back to the circuit here, right, it was equals to the operating diode current, the DC value, at the time varying, the change in the diode current. So I'm going to use the same thing, right? So our parallel equation is id of t is equals to id plus small id, and this id is the time varying component. Which initially we call it as delta id, remember. All right, so we can equate these two equations to find out that this small id is essentially equals to capital id vd over vt. Now I can further, sorry, small id equals equated to id over vt into vd. Now I can see that this parameter id over vt, its dimensions are of conductance, and this is also known as small signal conductance, right? So if I will take an inverse of this, so this is id over vt is a conductance, right? So if I will take an inverse of this, that will become a small diode, small signal resistance, right? So the inverse would be equals to small signal resistance. We define the small signal resistance as RD. So RD will become equals to VT over ID. So this is the value of the small signal resistance. It is also known as incremental resistance as well, also called incremental resistance. And also note down over here that the RD is inversely proportional to ID. All right, so this is the value. This is how we can solve that small signal analysis and find out the value of the RD And the value of the RD again is the small signal diode resistance is equals to the thermal voltage and the DC value of the diode current that is flowing through the circuit. So using that, we can find out the value of incremental or the small signal diode resistance. Now let's now what I want to do is I wanna draw the circuit on how we can potentially use it. Uh, okay, so let's look at that. Let's look at RD more. Let's go back to the IV characteristics that we draw. All right, in this IV characteristic, we saw that we have this tangent, right? And we wanted, and our slope was equals to 1 over RD. So we can also write down the slope as delta ID over delta VD here, right, at point Q. So this was equals to 1 over RD. So we can also equate it to, by using the equation over here, VT over ID will become inverse. It will become ID over VT. So this is something extra to remember by that this is equals to 6. So this means that the slope of tangent represents small signal conductance. All right. So by now we finalized that, okay, our value of the small signal diode resistance is VT over ID. So how we can use that thing in a circuit now? Okay, so let me make that circuit where we are all only talking about the small signal resistances. So when there was a small change in VDD, we get a small change in ID, and we get a small change in the potential drop across the diode. And this was a resistance. Rather than using a diode, now I modeled the diode as a resistance value. So this is our small signal approximation. Then when we are talking about these small changes in the input signal, I can model my diode as a resistance. If we go back to this circuit, we see that we initially included a diode here. So this diode will be replaced by a resistor if we are considering our small signal operation. Right, so this circuit can be used for determining incremental quantities we talked about. Delta ID, delta VDD, delta VD, right? It's a linear circuit. We can see that because of the resistances only now. And essentially, diode has been replaced by a resistor, RD, which is small signal diode resistance. Okay. Alright, so this is it for this lecture. In this lecture, we discussed about the small signal operation, and the take-home message of this lecture is that when we are talking about a small signal operation, in a diode circuit, we can replace the diode for that small in order to find those incremental quantities. We can replace the diode with a resistor RD, and we know the value of the resistor RD is equal to VT over ID. All right. So this ends the lecture. This lecture, and the next lecture, I'm going to do a couple of examples around small signal operation that will clear up these concepts more. All right. With that, thank you so much. I will talk with you in the next lecture.